Hello friends. So today we'll discuss about the important formulas in our module 1, also type 1 problems. So in module 1, so these are some of the formulas which are very important to solve any problems. So let's start. So first we have important formulas, topic important formulas. First, stress. As you know, stress is load acting through the cross-sectional area. So sigma, stress is given by sigma is equals to F by A, load by area, where load is in newtons and area is in mm square or meter square. So units are, so sigma is F by A. Unit for this are Newton per mm square, or also called as MPa, megapascal, or if it is area is meter square, it becomes Newton per meter square or just Pascal. Second one, second formula is strain. As we know, it is denoted by epsilon. So it's not strain nothing but change in length by original length. So change in length is in mm, original also length is in mm. So those both get cut off, and since there is no unit for strain, strain has no units, it is dimensionless. So strain, so this is longitudinal strain. Also the lateral strain may be change in diameter to original diameter, change in breadth to original breadth, etc. Third one is Hooke's law, also called as constant of proportionality, also called as Young's modulus. So as we know, Hooke's law, Young's modulus, is given by is denoted by capital E, and this holds good up to the elastic limit. So up to elastic limit, as we know that from the Hooke's law, stress is proportional to strain. That's why. So this proportionality constant is nothing but Young's modulus E, and formula is sigma by epsilon. Since stress by strain, S plus E equals to stress by strain, since epsilon has no unit, the unit of stress itself will become the unit of Young's modulus. Young's modulus, the unit is Newton per mm square, again same as stress, or MPa, or Newton per meter square, or Pascal. Next, fourth one, elongation of bar. So elongation of a bar, suppose we take a bar with a load attached to it, then elongation of bar can be measured using the formula that delta L, that is change in length, is equals to force F into the original length L upon A is the area of cross section of the bar into E is the Young's modulus. So the unit of elongation will be mm or meters. Elongation or shortening are both same, that is delta L equals to FL by AE. Next, fifth one, percentage elongation. So percentage elongation for a elongated bar, we can measure it from the formula LF minus LO all upon LF into 100, where LF is the final length after the load is applied after elongation. LO is the original area, that is before the load is applied, all upon final length into 100. So we get the percentage elongation. Next, sixth one, percentage reduction area. So percentage reduction area, as you know, when the bar is pulled, its lateral area is processually gets reduces. So this reduced percentage reduction can be found by the area found by the formula AO minus AF whole upon AO into 100, where AO is the original length before being loaded, minus AF is the final length after being loaded after elongation, all upon AO into 100. So we get the percentage reduction in area. Next comes the factor of safety. So as you know, factor of safety. So factor of safety for ductile materials is yield stress upon working stress. It's a ratio between yield stress upon working stress for ductile materials only. So the same factor of safety for brittle materials is ultimate stress upon working stress. It is a ratio of ultimate stress upon working stress for brittle materials. So proof stress is proof load upon the cross-sectional area. You get the proof stress. Then elongation of tapered rectangular cross-sectional bar is delta L FL. So for tapered rectangular cross-sectional bar, change in length delta L will be F into L upon T, capital E into A minus B log A by B. So where A and B are the breadth and thickness of the rectangular bar. So lastly, elongation of tapered circular bar. So elongation tapered circular bar is given by the formula delta L equals to FL upon pi by 4 d1 into d2 into E, capital E, where d1 is the smaller diameter, d2 is the bigger diameter of the taper, F is the load applied, L is the length of the taper, E is the Young's modulus. So these were the 9 very important formulas which we require in the subject. So very important formulas. Next, list of types of problems. So basically we should divide every problem into its own types, same types. So here I have divided all the problems into 9 different types. Although we will not going to solve all the 9. So we will solve at least the first 6 types. So type 1 is simple bar subjected to loading. A simple bar subjected to loading, we should find stress, strain, elongation on the bar. So type 2 are tensile test problems. In this we need to find the stress at yield point, stress at ultimate point, then Hooke's law, stress, strain, elongation, and breaking stress at the last. So type 3 are bars with varying steps. So in this type 3 we will have varying steps. So we have to find stress, strain in each step, each block, and we have to calculate the total elongation of the bars. Next, type 4 bars with varying cross section. So type 4, so bars with varying cross section means tapered circular or tapered rectangular bar. We have to find the change in length in such bars. Next, type 5 is elongation due to sulfate. So as you know, so there is a weight to every material. So due to its own weight, what could be the elongation we need to find? So we will find in this type 5. So lastly, type 6, principle of superposition problems, which are very important here. So we will solve. So what happens when a bar or member is subject to multiple loads in different directions? How to solve them? We will see in this type 6. So first we'll start with type 1, a simple bar subject to loading. As you can see, simple bar is subject to the load F on both the directions. It is being pulled apart, and D is the diameter of that bar, and that the same is, and the portion is the area of cross section. So to find the area of cross section, we use the formula pi by 4 d square, where if d is in mm, the area becomes mm square. If d is in meters, the area becomes in meter square. So similarly, area of hollow circular bar is given the formula area A equals to pi by 4 do square minus di square, where do is the outer diameter minus di is the inner diameter, the whole square. So this also is measured in units mm square or meter square based on the units of diameters. The area of cross rectangular bar, as you know, rectangular bar is a breadth into height or depth b into h. So this also is in mm square or meter square. Next, the stress mean formula. Once again, we have the stress formula sigma equals to P by A, also called F by A. So F or P both represents force in newtons. Stress is in unit Newton per mm square. Strain is delta L by L, since there is no unit for this, so it's dimensionless. Elongation of bar can be measured by the formula delta L equals to PL by E or FL by E, whatever. So P and F are same. So modulus of elasticity E equals to ratio of sigma by strain, epsilon or stress by strain, and the unit is Newton per mm square. So we'll take a first example 1. So a rod of 1.5 meter long and 200 meter diameter is subject to a load of 20 kilonewtons. If Young's modulus is 2 × 5 Newton per mm square, determine stress strain elongation of the rod. So length of the bar is 1.5 meters. So convert this into mm for easy simplification. Always need to convert everything in mm. So length is 1.5 meters, so 1500 mm. As we know, 1 meter is 1000 mm, 1.5 is 1500. D is diameter 200 mm. P is the load 20 kilonewton, converted to newtons, that is 20,000 newtons. E is Young's modulus 2 × 10⁵ Newton per mm square. So first stress, to find stress, sigma equals to P by A, 20,000 into pi by 4 d square. So we can use a calci and just find the answer. So substitute P, that is 20,000, area is pi by 4 d, instead of d substitute 200 square. Calculate the answer from a calci. Strain is delta L by L. So delta L, since we don't know the delta L here, so we can move to next formula. So extension elongation delta L equals PL by A. We can find delta L by this formula. So P is 20,000, L is 1500, A is pi by 4 200 square, and E is 2 × 10⁵. You will get the change in length here. We substitute, so change in length, that is in mm. Substitute this change delta L in that strain formula, you will get the strain. So example 2. A 25 mm rod diameter subject to a load of 50 kilonewton. Extension of rod is equal to 250 divisions on extension meter, where one division is 0.001 mm of case length. 200 mm, find E. So diameter is 25 mm. P is 50 kilonewton, that is 50,000 newtons. Change in length is 250 divisions and one division 0.001 mm. So that means change in length will be 250 into 0.001 mm. L length is 200 mm. So to find stress, so stress is load by area. So load is 50,000 upon pi by 425 square. In substitute in the calci, find the answer. Strain is change in length by original. So change in length is already given, that is 250 divisions, 250 into 0.001 upon 200. You get the strain. So next we'll take the third example. A solid alloy bar of 40 mm diameter is used if the permissible stress is 320 meganewton per meter square. So here the unit is meganewton per meter square, not to get confused. Newton per meter square is Pascal, so it becomes 320 MPa, megapascal. Determine capacity of the bar. If the hollow bar is internal diameter 20 mm is used, then the determine the outside diameter. Stress is 150 meganewton per meter square. So diameter D is 40 mm for solid bar, and sigma allowable stress sigma is 320 meganewton per meter square. And you have to find the load here. Hollow is 20 mm, sigma is 150, and you have to find DO. So for solid bar, with the formula stress equals to load by A, P by A, sigma is 320, P is unknown. You have to find this P, pi by 4 d square, that is 40 square. So therefore, substituting the answer, we get P equals to 2.124 kilonewtons. Similarly, first hollow bar, if you want to find the outside diameter, so sigma is P by A, P is pi by A is pi by 4 d square as di square. Sigma is 150, which is already given. P is the same load. They have just said the same load, so load is given we found just now. that is 402.124 kilonewton pi by 4 do square minus 20 square. So therefore, substituting all these values on a simplification, we have do equals to 61.7552 mm.